this episode, we're going to focus on the kinds of data problems that do not announce themselves loudly, but can quietly ruin a model's usefulness if you do not recognize them early. Beginners often think data quality means missing values, typos, or duplicate rows, and those do matter. But some of the most dangerous problems are more subtle because the dataset can look clean and still be misleading. Sparsity, multicollinearity, and leakage are three landmines that can make training results look better than reality, make models unstable, or make predictions fail when the model is used in the real world. Each one is a different kind of trap. Sparsity can hide signal and inflate confidence. Multicollinearity can confuse what the model is learning, and leakage can create a model that is essentially cheating. The goal here is to help you spot these issues using plain reasoning about how the data was generated and what information would actually be available at prediction time. When you learn to recognize these landmines, you start building models you can trust instead of models that only look good on paper. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. Sparsity means that most entries in a feature or matrix are zero, missing, or otherwise empty. And the important idea is that sparse does not automatically mean bad, but it changes how you interpret patterns. A common example is text or one-hot encoded categories, where you have many possible words or categories, but each row contains only a few of them. Another example is event data where most users do not trigger most events, so you end up with many columns that are almost always zero. Sparsity becomes a landmine when you mistake rarity for meaning, because a feature that appears only a handful of times might look highly predictive in a small sample, even if it is just noise. It can also create modeling difficulties when the feature space becomes huge relative to the number of examples, making it easy to overfit. Intentful EDA for sparsity is about asking how many non-empty values each feature has, and whether the rare non-empty values represent a real phenomenon or a data collection quirk. One reason sparsity is tricky is that it can be caused by the real world, like rare events, but it can also be caused by measurement design, like fields that are optional or systems that only log certain details under special conditions. If a column is mostly empty because a system only records it when there is an error, then the presence of a value is not just information about the world, it is information about the logging behavior. That matters because the model might learn to predict outcomes based on whether extra logging occurred rather than based on the underlying phenomenon you care about. Another sparsity trap is when missingness is not random, meaning the fact that something is missing carries information, like a form field left blank more often by a specific user group. That can be useful, but it can also create unintended bias if you do not understand why it is missing. The key is to treat sparsity as a clue about process, not just a spreadsheet annoyance. Multicollinearity is a different kind of landmine because the data can be complete and non-sparse, yet still cause confusion in how the model learns relationships. Multicollinearity means two or more features are strongly correlated with each other, often because they measure the same thing in slightly different ways. For example, total bytes transferred and total packets transferred might move together, or two different normalizations of the same raw count might end up telling the same story. When features are highly correlated, a model may struggle to decide which one deserves credit, and that can make parameter estimates unstable, especially in models that try to assign a clear weight to each feature. Small changes in data can cause large changes in those weights without changing predictive performance much, which is a sign the model is not learning a unique explanation. Even if you are not focused on interpretability, multicollinearity can make troubleshooting difficult because feature importance can bounce around unpredictably. Recognizing multicollinearity early keeps you from overinterpreting weights and keeps you from adding redundant features that do not truly improve the model. A beginner-friendly way to think about multicollinearity is to imagine that you are trying to guess which of two friends caused a surprise party, but both friends always show up together. You might correctly predict that the party happens when they arrive, but you cannot reliably attribute the cause to one friend or the other. In modeling terms, the model might use either feature to make predictions, and the choice can change from run to run depending on small noise. This is especially important in data AI because you often want to explain model behavior, not just achieve accuracy, and multicollinearity can undermine that explanation. It also matters for generalization because correlated features might not remain correlated in the future if the underlying process changes. If the relationship between the two features breaks, a model that leaned on one proxy might perform worse than expected. So multicollinearity is not just a math problem. It is a stability and interpretability problem. Leakage is the most dangerous of the three because it can make a model look almost perfect during training and testing while being useless in the real world. Leakage happens when the model is allowed to use information that would not be available at the time you want to make the prediction, or when the training process accidentally includes future data in a way that inflates performance. A simple example is using a feature that is recorded after an outcome occurs, like a resolution code that only exists after a ticket is closed, to predict whether the ticket will be escalated. Another example is computing a feature using the entire dataset, including test data, such as a target-based statistic that accidentally includes information from the future. Leakage can also be subtle, like using a timestamp that indirectly reveals the outcome because the outcome occurred at a known time and the data was collected after that. The defining trait is that the model is given unfair access to information that it would not have when deployed. Leakage often sneaks in because it is not always obvious which fields are future, especially when you have derived features that combine multiple columns. For example, a field like account status might be updated after an event, but the dataset might show the final status for all rows, making it look like a normal feature. A derived feature like days since last incident might be computed using logs that include events that happen after the prediction point, depending on how the dataset was assembled. Leakage can also occur through aggregation, such as computing customer-level averages across an entire time window, and then using those averages to predict an event that happens inside the same window. The model then indirectly sees information from after the event because the average includes behavior that occurred after the outcome. These are the kinds of leaks that are hardest for beginners because nothing looks obviously wrong, yet the model is quietly cheating. A practical way to detect leakage is to look for features that produce unbelievably strong separation between classes or unusually high performance that feels too good for the problem. If you build a simple baseline and it suddenly gets near perfect accuracy, that is not always impossible, but it should trigger suspicion and investigation. Another clue is a feature that has a direct logical connection to the label definition, like a field that is basically a restatement of the target in different words. You can also ask a timeline question for each feature. At the moment the prediction is supposed to be made, would this value exist yet, and would it be known to the decision maker? If the answer is no, then the feature is a leakage candidate. This timeline thinking is one of the most valuable habits in applied modeling because it protects you from accidentally building models that only work in hindsight. Sparsity, multicollinearity, and leakage can also interact, making the landmines harder to see if you only look for them one at a time. A sparse feature that is present only in rare cases might look predictive, but it could actually be a leakage feature that only appears after an event. For example, an error code might be logged only when a failure occurs, so its presence predicts failure perfectly, but that is not a valid predictor if the goal is early warning before the failure. Multicollinearity can hide leakage too, because you might remove one suspicious feature but keep a correlated proxy that still contains leaked information. Sparsity can also amplify multicollinearity issues in high-dimensional one-hot encodings, where categories are rare and correlated with other rare categories due to how the data was collected. Thinking about these issues together helps you see that data quality is not just about cleaning. It is about understanding how the dataset was formed. Another important point is that these landmines can distort evaluation, making you believe you have a strong model when you do not. Leakage is the most obvious culprit because it can inflate test performance, but sparsity can also cause evaluation to be unstable if the rare signals do not appear consistently across splits. A model might look great on one split because a rare but predictive pattern happened to fall into the training set, then fail on another split where that pattern is absent. Multicollinearity can make evaluation appear stable while hiding the fact that the model's internal reasoning is unstable, which becomes visible when you try to interpret feature importance or when you deploy into an environment where feature relationships shift. The deeper lesson is that evaluation numbers are only meaningful if the data structure and features reflect what would happen in real usage. Data quality landmines can break that link, so the model is being graded on a test it will never take again. You can also connect these ideas to simple checks that fit into an EDA mindset without becoming implementation heavy. For sparsity, you can look at how many non-empty values exist per feature and whether many features have almost none. For multicollinearity, you can examine correlations between numeric features and watch for pairs that move together nearly perfectly. Then ask whether those pairs represent redundant measurements or derived copies. For leakage, you can review feature definitions and data lineage, meaning where each column came from and when it would be known, and you can be suspicious of features that are created from outcomes or post-outcome actions. Even without writing code, you can practice this reasoning by reading a data dictionary, examining sample rows, and thinking like a time traveler who must make predictions without future knowledge. The key is that these landmines are conceptual first and technical second. By the end of this topic, you should see sparsity, multicollinearity, and leakage as three distinct warnings about the relationship between data and reality. Sparsity warns you that rarity can be mistaken for signal and that missingness often reflects how data was captured. Multicollinearity warns you that redundant features can make models unstable to interpret and sometimes fragile to future shifts, even if accuracy seems fine. Leakage warns you that a model can cheat by using future information, producing performance that collapses when deployed. When you learn to look for these issues early, you save yourself from wasting time tuning models that are built on shaky ground. More importantly, you build the habit of treating modeling as a careful translation from the real world into data, and the quality of that translation is what ultimately determines whether the model is trustworthy.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.